Hello, everybody. We got kind of a random array of questions, and we'll go through them just one by one, and I'll try to treat them just as sort of both specific, but also talk a little generally about the issues surrounding these topics. A couple of the things are a little on the complicated or open-ended side, so I'm going to talk about them in a way that I think fits to the exam. But then we'll try to provide some links later on that you can link to sort of more specific information that's a little hard to do in this kind of context. So I say, let's just dive right in. Let's see here. There we go. Okay. The first question that came through was, could you talk a little bit about panel points for joists and trusses? So panel points are kind of an interesting concept because, well, trusses are an interesting concept, right? If you have a truss, the gist of the idea, sorry, this is the world's worst drawing of a truss, but the gist of the idea is that I have a structural member, and I'm just going to talk about trusses in terms of beams for now. I find that when you're talking about these topics, it's easier to think about it in beam form than getting into all the other complications, and we can talk about it more generally that way. So the whole point of any sort of type of beam really is span, and to get span, what we really want is depth. That's what you're really looking for when you're trying to get span. That's how you get stiffness, that's how you get the capacity to span longer distances. And so while thinner, less depth material can span pretty far, depending on if it's steel or if it's certain kinds of wood, the game is always, can I get more depth compared to the amount of weight of steel, or compared to the amount of like how big a tree would I need, et cetera, to get it to have more depth. And so the truss is the way that you get that. And the trusses can span anywhere from like a floor truss. For like a wood frame house, you might use a floor truss made out of 2x4s, where each of the members is made out of a 2x4, and that might span anywhere from, say, 18 feet to 26 feet or 30 feet even, all the way up to really giant steel trusses that, or concrete trusses that can span hundreds of feet. So the idea of the truss is a very flexible, used in all kinds of different settings. But the gist of it is I'm looking for as much depth as I can get for the amount of material that we're using. And it's broken up into these triangles because the whole point of the truss is that the triangles are the most solid of the shapes. The triangle can't be broken down. So as each piece tries to be sort of pushed over, the triangular shape can't. It can't deform into anything else. The only way that the triangle can deform is by the members, the actual lines that make up the triangle. Those can break or deform, but the triangle shape itself can't. So the truss is always a series of triangles. And with the truss, any one of these pieces, the whole point is that any one of these pieces is actually a relatively small member. And so I have small members at the, on the inside in what's referred to as the web members, and small members at the top and the bottom, which are the chord members. And by putting these all together in these triangular shapes, which can't deflect easily, can't deform easily, allows us to span really pretty impressive distances with very, very small individual members, because they are now made to become one very deep member. So when you start to think about that, you realize that any one of these moments, as I said, like let's say the top chord there, that top chord in a wood truss for a house, like I said, could easily be a 2x4 on its side. Well, if I started to put a giant load directly onto that 2x4, that 2x4 is going to start having its own set of problems, right? It's not going to be that the overall truss is now loaded. The question will be, can that 2x4 hold that particular load? Let's say it was a giant air conditioning unit or something like that. So what I want to do, if I can, is instead of putting a load just kind of randomly located on the truss, I want to put a load right where some of these pieces are. Sorry. So I'm going to have that load. In this case, I'm hanging one. Maybe here I'm loading from the top and coming right down. And you'll see that I'm pointing directly at where these different members, the web members and the cord members, come together. Those are the panel points. The reason they're called panels is because each of the triangles is called a panel. So they're talking about the nodes where these things come together. They'll also be referred to as nodes. But panel point is specific in referencing the place to load. So the point of that is that each of these members, as they come together, the web pieces and the cords, the top and the bottom cords, are connected in pin joints. So the forces will always be sort of thrust straight through all of those lines of those webs and on the cords. There's no moments set up in the individual pieces. This is why they can all function so lightly and so simply. And so the forces, when you load directly onto a panel point, will create a situation where the force is equally spread through the whole thing and is not then reliant on the strength of the individual member. So that individual top or bottom cord can be a much lighter member because you're not trying to load directly onto that. You're loading on the overall member, and you know that because you're loading the panel point. You're loading the spot that allows it to spread that load through the top cord, through the web members that come to that node, and then eventually to the bottom cord that is also connected to those web members. And so it spreads that load through the whole system in the way that it's meant to be spread. So that idea of the panel point is really just that the whole point of the truss is to use very, very light members as much as you can, but get a lot of depth out of the overall truss, and therefore making sure that you don't accidentally load that truss in a way where the individual tiny member breaks, therefore making the whole big member not function. You don't want the whole truss to fail because you put the load for the air conditioner, or not air compressor or something, onto that wrong part of that truss. So trusses are incredibly simple idea, but you have to use them carefully because that if you load them incorrectly, they will fail dramatically. Now, obviously, there's a lot of different versions of trusses. There's sloping trusses. There's scissor trusses. There's a whole series of different types of trusses. There's a lot of online material showing you different examples. The concept holds true no matter what. You're always loading at the point where those loads can be spread to the other members and not where any one individual portion is taking the whole load. One little caveat to all of this, this is sort of what I always refer to as the architect's truss, is the idea of the Viren truss, which I'm going to draw another terrible truss here. Viren truss looks like this. I'm sure you've seen it, that those are supposed to be straight lines and perpendicular lines. The Viren truss is not a truss, but it's called a truss for some historical reason that I have no idea why. In this case, each of these nodes is actually a moment connection, and the diagonal pieces in the triangles are gone, which is why it's not actually a truss. The reason I mention it is that you still call these panel points, and there's still a reason why you might want to load on those direct panel points, having to do with spreading the overall load. But the main reason I mention it is that whenever you talk about trusses, the Viren truss is one of those weird ones that has a very specific name, and therefore you can often get a question about it. It's worth kind of just knowing what it is, but also knowing that it's not a real truss, right? pretty much all the other trusses, you'll still follow all of the same basic, whether the top chord and the bottom chord are parallel. Doesn't really matter as long as there are triangles, as long as the overall system is made out of pin joints, and as long as the loading is done on the panel points. That's all still considered a truss, no matter what the shape is.
Today's A.R.E. Live episode is an extension of our online A.R.E. curriculum that you can find on blackspectacles.com, the home of online learning for architecture and design. If you need to prepare for the A.R.E., which I assume many of you guys do, and if you're looking for a good way to study for the exam that's more flexible and easier to digest than the traditional exam prep materials, and head over to blackspectacles.com to try out any of our free A.R.E. video tutorials that are taught by tonight's presenter, Mike Newman, and that are built in collaboration with AIA Chicago. As an attendee, and as you can see here on the screen here, we have a couple of notes or information for today's episode. Anyone who is attending today's session, you're eligible to use this coupon code worth 15% off the first charge on your individual membership. If you're one of those folks who would like for your firm to purchase Black Spectacles Access for you and your colleagues, just visit blackspectacles.com/business, which is this fourth link here, and we'll send all the information for your firm to get set up. And also from now until the 15th of next month, firm memberships are 15% off if you mention this episode when you submit your form through blackspectacles.com/business. Also on this, you'll see that our next webinar will be on May 27th with Mike at 6 o'clock. So if you'd like to register for it, here's the registration link. We're still firming up the details and the actual topic. So if you have any suggestions and would like Mike to cover a specific topic or would like us to interview someone in particular about a specific topic, please let us know.